In the next two videos we're going to see how Moivre's theorem can be used to obtain useful trigonometric identities. Our work is going to involve not only a knowledge of Moivre's theorem but also the ability to use Pascal's triangle efficiently. So let's plough straight into an example. If we have a look at Moivre's theorem, we know that Moivre's theorem tells us that cos theta plus I sine theta to the power 5 is equal to cos phi theta plus I sine phi theta. Now, if we want to expand a plus b to the power 5, we need the fifth row of Pascal's triangle, which is 1, 5, 10, 10, 5, 1. So, cos theta plus I sine theta to the power 5 is going to be one lot of cos theta to the power 5, in other words cos to the phi theta, plus 5 lots of cos to the 4 theta times by I sine theta, plus 10 lots of cos cubed theta times by I sine theta squared, plus 10 lots of cos squared theta times by I sine theta cubed, plus 5 lots of cos theta times I sine theta to the power 4, plus 1 lot of I sine theta to the power 5. Now, if we introduce the shorthand cos theta equals c and sine theta equals s, that will save us quite a lot of writing. So the line above becomes c to the 5, cos theta plus I sine theta to the power 5 equals c to the 5, plus 5 lots of c to the 4 times is, plus now the next term is going to be 10 cos cubed theta, so that's 10c cubed, times by I squared s squared, plus 10c squared times by I cubed s cubed, plus 5c times I to the 4 s to the 4, and finally I to the 5 s to the 5. Now we know that I squared is minus 1, so I cubed is I squared times I is minus I to the 4 is I squared times I squared, which is minus 1 times minus 1 is plus 1. And I to the 5 is I to the 4 times I, which is 1 times I, which is I. So, we've got c to the 5 plus 5i times c to the 4s minus 10 c cubed s squared minus 10i c squared s cubed plus 5 cs to the power 4 plus is to the power 5. And if we collect together the real terms and the imaginary terms, the real terms are the c to the 5 minus 10 c cubed s squared plus 5 cs to the power 4. And then the imaginary terms, well, factor out the I, we've got I times 5 c to the 4s minus 10 c squared s cubed plus s to the 5. So what that tells me is that cos phi theta plus I sine phi theta, which is, we know is the same thing by Moivre's theorem as cos theta plus I sine theta to the power 5, is the same thing as c to the 5 minus 10 c cubed s squared plus 5 cs to the power 4 plus I times 5c to the 4 s minus 10 c squared s cubed plus s to the 5. Okay, so there's that result again. Now let's just look at the two bits separately. If we look at the real bits, we've got on the left hand side cos phi theta equals c to the 5 minus 10 c cubed s squared plus 5c s to the 4. But I know that cos squared theta plus sine squared theta is always equal to 1. So s squared is the same thing as 1 minus c squared. So we've got cos phi theta can be rewritten as c to the 5 minus 10 c cubed times by not s squared but 1 minus c squared plus 5c. Now s to the 4 is the same thing as s squared squared, so that's the same thing as 1 minus c squared squared. So we've got cos phi theta is the same thing as c to the 5 minus 10c cubed times 1 minus c squared plus 5c times by the expansion of 1 minus c squared squared, which is 1 minus 2c squared plus c to the 4. Now tidying this up, if we first of all look at the c to the 5 terms, we've got c to the 5 minus 10 c cubed times minus c squared, so that becomes plus 10c to the 5. And then I've also got from the final bracket plus 5c to the 4, 5c to the 5. Similarly, if I look at the c cubed terms, I've got minus 10c cubed from the first bracket and another minus 10c cubed from the second bracket. And then if we look at the c terms, I've just got plus 5c from the final bracket. So I've got cos phi theta is 16c to the 5 minus 20c cubed plus 5c. Doing a very similar thing with the sine, with the imaginary terms, to obtain an expression for sine phi theta, we can obtain sine phi theta equals 5c to the 4s minus 10c squared s cubed plus s to the 5. This time, the fact that cos squared theta plus sine squared theta equals 1 tells me I can write cos squared theta equals 1 minus sine squared theta. So I've got 5 times by cos to the 4 theta, or cos to the 4 theta is the same thing as cos squared theta squared, so that's 1 minus sine squared theta squared, times by the s, minus 10 lots of 1 minus sine squared times s cubed, plus s to the 5, expand the 1 minus s squared squared to obtain 1 minus 2s squared plus s to the 4, and simplifying the right hand side will give me sine phi theta equals 5s minus 20s cubed plus 16s to the power 5. So, summarising our results from the previous page, we've now got that cos phi theta can be written as cos to the 5 theta minus 10 cos cubed theta sine squared theta plus 5 cos theta sine to the 4 theta, or as 16 cos to the 5 theta minus 20 cos cubed theta plus 5 cos theta. And we've also seen that sine phi theta can be written as 5 cos to the 4 theta sine theta minus 10 cos squared theta sine cubed theta plus sine to the 5 theta, or as 5 sine theta minus 20 sine cubed theta plus 16 sine to the 5 theta. And finally, making use of these results, we can also obtain a useful expression for tan phi theta. Now tan phi theta is sine phi theta divided by cos phi theta, and if we use equations 3 and 1, we can write that as 5 cos to the 4 theta minus 10 cos squared theta sine cubed theta plus sine to the 5 theta divided by cos to the 5 theta minus 10 cos cubed theta sine squared theta plus 5 cos theta sine to the 4 theta. If we now divide top and bottom of this fraction by cos to the 5 theta, then we're going to obtain that rather monstrous looking expression. If you look carefully at it, the top line now becomes 5 sine theta over cos theta, in other words 5 tan theta, minus 10 sine cube theta over cos cube theta, in other words 10 tan cube theta, plus sine to the phi theta over cos to the phi theta, in other words tan to the phi theta. The bottom becomes 1 minus 10 sine squared theta over cos squared theta, in other words 10 tan squared theta, plus 5 sine to the 4 theta divided by cos to the 4 theta, in other words 5 tan to the 4 theta, which gives me then 5 tan theta minus 10 tan cube theta plus tan to the phi theta over 1 minus 10 tan squared theta plus 5 tan to the 4 theta. So we've got a fifth identity there. So we've now got identities for cos phi theta, sin phi theta, and tan phi theta. So we might use these identities, for instance, to solve an equation like cos 5x plus 10 cos x cos 2x equals 0. So making use of identity 2, we can replace the cos 5x by 16 cos to the 5x minus 20 cos cubed x plus 5 cos x plus 10 cos x times by cos 2x, but I know that cos 2x is the same thing as 2 cos squared x minus 1. And that all has to equal 0. So tidying that up then, we've got 16 cos to the 5x minus 20 cos cubed x plus 5 cos x plus 20 cos cubed x minus 10 cos x must equal 0. In other words, we've got 16 cos to the 5x minus 5 cos x equals 0, or cos x times by 16 cos to the 4x, take away 5, must equal 0, which tells me that either cos x equals 0 or cos x equals plus or minus the 4th root of 5/16. So the first equation, cos x equals 0, gives me x equals pi by 2 and 3 pi by 2. Cos x equals the 4th root of 5/16, gives me 0.726 or 5.557. And cos x equals the minus the 4th root of 5/16, gives me x is 2.415 and 3.868. And in this case I've found the solutions clearly in radians, and I found the solutions between 0 and 2 pi. Okay, so our first example then is which is going to follow very similar lines to what we've just been doing. Use Demoivre's theorem to prove that cos 4 theta is equal to 8 cos to the 4 theta minus 8 cos squared theta plus 1, and hence solve the equation cos 4 theta plus 3 cos 2 theta plus 2 equals 0 for values of theta between 0 and 2 pi. Okay, well, Demoivre's theorem tells me that cos 4 theta plus I sine 4 theta is equal to cos theta plus I sine theta to the power 4. If I introduce the shorthand c equals cos theta and s equals sine theta, then I've got cos 4 theta plus I sine 4 theta is c plus is to the power 4. Using Pascal's triangle, that's 1 lot of c to the 4 plus 4 lots of c cubed times is plus 6 lots of c squared times is squared plus 4 lots of c times is cubed plus 1 lot of is to the power 4, which is c to the 4 plus 4i c cubed s minus 6 c squared s squared, because I squared is minus 1, minus 4c s cubed I, because I cubed is I squared times by I, which is minus I. And then finally, I've got one lot of I to the 4 s to the 4, but I to the 4 is just 1, so that's plus s to the 4. Looking at that, really what we're only interested in is cos 4 theta, which is the real side on the left hand part. So if we equate the real side on the left hand part, that should equal the real expression on the right hand side. So we should have cos 4 theta equals c to the 4 minus 6c squared plus s to the 4. That's all of the terms which haven't got an I in it. Again, now we just need to remember that cos squared plus sine squared is always equal to 1, so sine squared can be replaced by 1 minus cos squared. So I've got c to the cos 4 theta equals c to the 4 minus 6c squared times by s squared, which is 1 minus c squared, plus s to the 4. Well, s to the 4 is s squared squared, which is 1 minus c squared squared. So that's c to the 4 minus 6c squared times by 1 minus c squared, plus the expansion of 1 minus c squared squared is 1 minus 2c squared plus c to the 4. And tidying that all up now, we've got c to the 4 minus 6c squared plus 6c to the 4 plus 1 minus 2c squared plus c to the 4. In other words, we've got 8c to the 4 minus 8c squared plus 1. And that is precisely what we want when we remember that c just stands for cos theta. So part A of the question has been done fairly efficiently. So we've now got to solve the equation cos 4 theta plus 3 cos 2 theta plus 2 equals 0, and finding values between 0 and 2 pi for that equation. So, making use of what we've already just proved, we've got cos 4 theta can be replaced by 8 cos to the 4 theta minus 8 cos squared theta plus 1. Cos 2 theta we know is the same as 2 cos squared theta minus 1. So I've got 8 cos to the 4 theta minus 8 cos squared theta plus 1 plus 3 lots of 2 cos squared theta minus 1, add 2 must equal 0. So if we tidy that up, that becomes 8 cos to the 4 theta minus 2 cos squared theta equals 0. So we've got cos squared theta and 2 as a common factor. So I've got 2 cos squared theta times by 4 cos squared theta minus 1 must equal 0, which gives me either cos theta equals 0 or cos theta equals plus or minus a half. So my solutions are, for cos theta equals 0, I've got theta equals pi by 2 or 3 pi by 2. For cos theta equals a half, I've got theta equals pi by 3 or 5 pi by 3. And for cos theta equals minus a half, I've got 2 pi by 3 or 4 pi by 3. And for our next example, we're going to say, right, if t equals tan theta, use de Moivre's theorem to prove that tan 3 theta must equal 3t minus t cubed over 1 minus 3t squared. And then use that to solve an equation and deduce some exact values. So let's make a start with the first part of the question then. So we're being asked to consider tan 3 theta. Well, de Moivre's theorem tells me all about cos 3 theta and sin 3 theta. So the way we'll start this off is by saying that we know that cos 3 theta plus I sin 3 theta is the same thing as cos theta plus I sin theta cubed. That's de Moivre's theorem, which is equal to c plus is cubed, where c is cos theta and s is sin theta. So, expanding out, we've got cos 3 theta plus I sine 3 theta must be 1 lot of c cubed plus 3 lots of c squared times is plus 3 lots of c times is squared plus 1 lot of is cubed, because the third row of Pascal's triangle is 1, 3, 3, 1. Tidying this up a little bit, we've got c cubed plus 3i times c squared s plus minus 3 c s squared, because I squared is minus 1. And then I cubed is I squared times I, so that's minus 1 times I. So I cubed s cubed is minus I s cubed. Collecting together the real terms and the imaginary terms, we can see then that the real terms tell me that cos 3 theta is the real term on the left hand side. The real term on the right hand side is c cubed minus 3c s squared. And looking at the imaginary terms, on the left hand side the imaginary term is the sine 3 theta, and on the right hand side the imaginary term is 3c squared s, take away s cubed. Now tan 3 theta is sine 3 theta divided by cos 3 theta. So that is 3c squared s minus s cubed divided by c cubed minus 3c s squared. And at this stage we need to divide the top and the bottom of this fraction by c cubed. If I do that, I'm going to end up with 3c squared s divided by c cubed minus s cubed divided by c cubed over c cubed divided by c cubed, take away 3cs squared divided by c cubed. Now, c squared s divided by c cubed just gives me s over c. S cubed over c cubed, I can't do anything with at all. C cubed over c cubed gives me 1. And cs squared divided by c cubed just gives me s squared over c squared. So my simplified form of this fraction, remembering that s over c is simply equal to tan theta, in other words t, I have got now that the tan 3 theta is 3t minus t cubed over 1 minus 3t squared, as required. Show that the substitution t equals tan theta enables this equation t cubed minus 3 root 3 t squared minus 3t plus root 3 equals 0 to be rewritten as tan 3 theta equals root 3, and hence solve the equation. So, looking at the equation that we've got, if we take the terms not involving the root 3 onto the opposite side, we obtain root 3 minus 3 root 3 t squared is equal to 3t minus t cubed. And then taking out the factor of root 3 that we've got root 3 times by 1 minus 3t squared equals 3t minus t cubed. In other words, we've got root 3 is equal to 3t minus t cubed over 1 minus 3t squared. But from what we've just done, 3t, if t is tan theta, then 3t minus t cubed over 1 minus 3t squared is precisely tan 3 theta. So I've got the equation tan 3 theta equals root 3. Now, I know that if I've got tan 3 theta equals root 3, then 3 theta could be pi by 3. It could be pi by 3 plus pi, so that's 4 pi by 3. It could be pi by 3 plus 2 pi, which is 7 pi by 3. It could be pi by 3 plus 3 pi, which is 10 pi by 3, etc. So, theta could be pi by 9, or 4 pi by 9, or 7 pi by 9, or 10 pi by 9, etc. So tan theta, or the value of t, is either tan of pi by 9, or tan of 4 pi by 9, or tan of 7 pi by 9. Tan of 10 pi by 9 is actually an exact repeat of tan of pi by 9, because we know that tan has a period of pi. It repeats every pi. Similarly, tan of 13 pi by 9 would be exactly the same as tan of 4 pi by 9. So we've only got those 3 different values of t. So we've found the exact solutions of the cubic equation, and the exact solutions to that cubic equation are t equals tan of pi by 9, tan of 4 pi by 9, or tan of 7 pi by 9. Okay, right, so deduce the exact values of, first of all, tan of pi by 9, tan of 4 pi by 9, tan of 7 pi by 9, and then secondly, tan squared pi by 9, tan squared 4 pi by 9, and tan squared 7 pi by 9. Well, we know that if we call those 3 values, the 3 roots, alpha, beta, and gamma, then alpha, beta, and gamma are the roots of t cubed minus 3 root 3 t squared minus 3t plus root 3 equals 0. And from work that we have done in Unit 1 of the Further Maths, we know that for a cubic equation, alpha plus beta plus gamma is equal to minus b upon a. So that's the negative of the coefficient of t squared divided by the coefficient of t cubed. So in this case, it's the negative of minus 3 root 3 over 1. In other words, it's equal to 3 root 3. We also know that alpha beta plus beta gamma plus gamma alpha is equal to the coefficient of t divided by the coefficient of t cubed. It's c upon a, if you like. And in this case, that is minus 3 over 1, which is minus 3. And we also know that alpha times beta times gamma is going to be equal to the negative of the constant term divided by the coefficient of t cubed. In this case, minus root 3 over 1. So we get minus root 3 for the value of alpha, beta, gamma. So for part 1 of the question, tan of pi by 9 plus tan of 4 pi by 9 plus tan of 7 pi by 9 is simply alpha plus beta plus gamma, which we know is 3 root 3. Tan squared pi by 9 plus tan squared 4 pi by 9 plus tan squared 7 pi by 9 is alpha squared plus beta squared plus gamma squared, which is the same thing as alpha plus beta plus gamma all squared. Take away 2 lots of alpha beta plus beta gamma plus gamma alpha. So that is 3 root 3 squared, which is 27. Take away 2 times minus 3, which is take away minus 6. So we've got 27 minus minus 6, which gives us 33. Rather neat link up between de Moivre's theorem and the roots of polynomials work that you did back in Unit 1. In the next video, we'll be looking at some further connections between de Moivre's theorem and trigonometric identities.